And thanks to all the organizers for giving this opportunity. It's a pleasure to be back here in Bonn. Before we get started, let me just say one thing. The technician has suggested to try to do the lecture using only the ambient microphones in the room. If there are problems hearing me, then we can try the headset. He suggested to try the ambient microphones first before using the headset. So please, those of you that are listening, especially via the transmission over the internet, please somebody speak up if it's not really audible, okay? All right, so first of all, let me issue a disclaimer. There was a little bit of false advertising in my title. I originally intended to sort of give a little bit of a survey of what has been done with respect to the Olympics situation, and then talk about the parabolic case. And then I realized that that might be a bit ambitious. It might involve sort of doing a lot of hand waving, and I decided that for a mini course it was maybe more appropriate to just focus on the caloric case, the parabolic case, because that's where there's a lot yet to do and there's a lot that's not yet known. And that way I can sort of fill in some background, give some details. I thought that would be more appropriate for a mini course. That means also that at the beginning, they're going to be reviewing some material from parabolic equations, that for people who are knowledgeable in that area, maybe a bit of a boring synopsis of things that you already know. Hopefully we'll get to things more interesting as we go on. On the other hand, for those of you that are not familiar with parabolic equations, I think it's probably good to take this approach. All right, so let me begin by sort of stating what we're interested in. So let's consider the Dirichlet problem with data in LP. That's what the P stands for. So we're going to be doing this for the heat equation. So we're going to be seeking a solution to the heat equation in a domain omega. Omega is going to be contained in, for me, Rn plus 1, which is space-time, parabolic space-time, Rn plus R. The last variable will be the time variable. Okay? And we're going to say that U restricted to sigma. I'll tell you what sigma is in a second. There's going to be an LP of sigma. Sigma is going to be something called a lateral boundary. In parabolic world, boundaries are more complicated than in before. I'll come back to that in a little bit. Okay? And we're going to look at, and we're going to want that the non-tangential maximal function of U belong to LP on sigma. Okay? So what's the non-tangential maximal function? It means that at a point on the boundary, you're taking the supremum of U, or the absolute value of U, within a parabolic cone. Okay? Here, this is the right problem to look at if sigma is of infinite extent in the time direction. Oh, and by the way, for me, time is going to run horizontal, which is kind of an avant-garde thing to do. We're a little parabolic people, but it's going to be kind of convenient for us to think of things that way. All right? And the measure on sigma that we're going to look at, the surface measure, we'll denote it as sigma. And this is going to be two ways to think about it. This will be parabolic n plus one-dimensional Hausdorff measure restricted to sigma. So what is parabolic Hausdorff measure? So it's defined the way usual Hausdorff measure is, except you cover, instead of by standard cubes, by parabolic cubes. What is a parabolic cube? It has dimensions r in all the spatial directions and r squared in the time direction. And when are we choosing n plus 1? So this is, okay, our ambient dimension is n plus 1. So the boundary, morally speaking, is an n-dimensional object. And the homogeneous dimension of parabolic Rn is n plus 1, because if you have n minus 1 spatial dimensions of r and then a time dimension of r squared, then the total mass here is the total volume here is r to the n plus 1. So you're defining this guy in the way you would define the usual Hausdorff measure, but again, you just take parabolic cubes or sets of parabolic diameter in most of certain size, all right? Okay, and the thing that you raise the diameter to is this power, all right? And it turns out a lot of times, not all the time, but many times, and for us in particular, in the context we're going to be talking about in these lectures, this is the same as, or at least equivalent to, the following thing you take. Standard n-1 dimensional Hausdorff measure, restricted to sigma t. This is the time slice. In other words, the cross-section of sigma with t pegs. And then you integrate it in t. Okay? These aren't always the same, but for our purposes in these lectures, these are the same. Okay? And in the setting of parabolic problems, it's kind of more standard and maybe a little more natural to think about the so-called initial Dirichlet problem, which is the same idea. But now, we're going to assume initially that the solution is 0. And again, we're going to look for non-dimensionalities on the lateral line. Okay, so all we're doing here is we've got this domain here with time running this way, and you're just cutting it off here at t equals 0. We're starting off with a solution that's initially 0, and then we let it evolve as time goes forward, specifying data here on the left. Okay? All right? And the interface is dp, or initial Dirichlet function. To do this for p finite, for some, well, yeah, for p finite, let me say it that way. This turns out to be equivalent to saying that the caloric measure, and we'll say a bit in a moment what that is absolutely continuous with respect to surface measure, and the Radon-Nikodym derivative is in reverse Taylor class with exponent q, and q is dual to p. Okay. All right. So reverse Taylor classes, that just means that, let me call this K. And we take the LQ average. It's going to be controlled by the L1 average. Okay. Here, delta. What is delta? Delta equals surface cube. So the idea is that you're going to take a parabolic cube I centered on the boundary And then delta is the intersection of either level. Okay? All right, the way I've stated this is in the case that the caloric measure satisfies a doubling property, which for us, for purposes of these lectures, that's always going to be the case. Okay, we'll come back to that in a second as well. All right. I realized I should have, no, I guess not. I wonder if I should erase these things sooner, but I guess probably that's not the right thing to do. Now we have some drying time.
In the case, if you tell me, like there is a metal property you can just do.
Sorry, what? The squeegee here?
Yeah.
Oh, yeah, the dry fast. Maybe I should use my phones more efficiently now, because I'm going to be erasing a lot. Running too big. Okay? So, why is this thing equivalent to this reverse Seller condition with exponent q equivalent to solving the Dirichlet problem? I'm not going to go into the details of that, but the heuristic is pretty straightforward. You want to be able to, oh, I need to tell you one thing though, okay? So, make a comment about caloric measure. This is actually a measure that for points xt in the domain, we construct a solution u of xt by integrating on sigma the boundary data integrated against caloric measure. Okay? So it's a measure that produces the solution. Okay? In the same way that harmonic measure produces a solution to the classical Dirichlet problem for the Laplacian. All right? And this thing exists by Wiener, Bailey Wiener, Perron Wiener, Brelow method. I won't get into that. We're going to take for granted that this exists. See a bit more about that in a moment. But the idea here is that in order to be able to plug in LP data, then this better be absolutely LP with respect to sigma. Then this better be absolute continuous with respect to sigma. The density better be an LQ. And this LQ condition, this reverse Seller condition, just gives you the right scale invariance that gives you the non-tangential estimates. Okay? All right. So, in fact, there's a Wiener criterion. In the caloric case, due to Evans anxiety, goes back to 82. It tells you when, it characterizes the domains for which, that are regular for the heat equation, meaning that if you plug in continuous F, the solution that you produce is going to be continuous all the way to the boundary. Okay? And a question might arise, what about the case of singular data? Okay, and that's why we look at the LP problem. Okay, so the LP for some p less than infinity. Okay. All right. So what I'm really going to be talking about in these lectures is not just solving the Dirichlet problem in a given domain per se. It's more about the question of for which domains can we solve the Dirichlet problem in this sense. Okay? Or is singular data in LP. All right? Okay? And it turns out that in the elliptic, or at least the harmonic case, we now have a good answer to this. We basically have a necessary and sufficient criteria. Here's the characterization. This is joint work with Jonas and Zong, Philip Martel, and Hofmann. You. Johnny Tulsa. Me. I won't say much more about that. Just that, okay, just rather recently, within the past couple of years, we can give a pretty definitive answer to the question of sort of having an analog of the Wiener criterion with singular data instead of continuous data. Okay, but what about the parabolic case? And in that setting, the state of the art is much more primitive. We know a lot less than we do in the case. So what I'm going to talk about today, or in these lectures, is some sort of initial progress in that direction. Okay? All right. So first, let me provide a bit of context here. Okay, so there's this classical result of Dahlberg in 77, where he showed that dp, in fact, d2 with b equals 2 is solvable for the Laplacian. This is an elliptic problem. In a Lipschitz domain. So Lipschitz domain, that just means that the domain is locally the region above a Lipschitz graph. All right? With some kind of finite number of coordinate patches being required to cover that. Okay? So following the result of Dahlberg, there was a conjecture of Hunt was that the same should be true for the heat equation in a lip 1/2 domain. Okay, so which is the analog of a Lipschitz domain in the parabolic setting. Locally, the domain is given as the region above the graph of a lip 1/2 function. Lip 1/2 means the graph of a function a of xt, which satisfies A of xt minus A of ys is less than or equal to some constant, the parabolic distance from xt to ys, and this is defined to be the usual length of the space variables plus the square root of the time variable. Okay. For my purposes, since these lectures we're going to be talking exclusively about the parabolic setting, I'm just going to call this Lipschitz. Okay. So when in this context, unless I specifically say something to the contrary, Lipschitz means parabolic Lipschitz. So honest Lipschitz in the space variable, lip 1/2 of the time variable. Okay. So anyway, Hunt conjectured that in that setting, and it was natural for the point of homogeneity, the Dahlberg's result could carry over for the heat equation. And that seemed like a good, based on homogeneity, that seemed like a good conjecture, but it turned out to be false. So in fact, this was false. There's a counterexample using Hofmann and Wu. This was published in '88. Okay, so they produced an example of a parabolic Lipschitz domain for which the caloric measure and the surface measure are mutually singular. Okay, so no way can you get an analog, a parabolic analog of Dahlberg's there in that setting. Okay, so when could you get such a thing? So there was a major breakthrough due to John Lewis and Margaret Murray in '95. They showed that dp or IdP are solvable for what I'll call regular parabolic Lipschitz domains. Now I'll just abbreviate this R-lit. Okay, now what does that mean? Okay, so this is locally the region above the graph of a function A of xt that is Lipschitz, honest standard Lipschitz in x, and in a time variable, we're going to assume the following condition, that first of all, I'm going to define a half-order time derivative, which I'll denote by dn in the following way. Okay? It's n because the way I'm writing things, t is the nth variable. It's going to be the h for me in these lectures is going to denote the standard heat operator. So h to the minus a half is a parabolic fractional integral it has parabolic order 1 or minus 1, smoothing by parabolic order 1, which means exactly 1 order in a space variable and half an order in time. So you're taking the negative square roots of the heat operator. Okay? So this smooths by half an order in time in particular, and you compose it with a full time derivative, and the net effect is half an order of differentiation in time. Okay? And the R-limit condition is that in addition to being honestly Lipschitz in the space variable, you also have that dn of A should be BMO. And here BMO is parabolic BMO. Okay, meaning that it's defined as in the same way as the usual BMO, but now you take averages with respect to parabolic cubes instead of standard cubes. Okay? So it turns out that R lib implies lib. This is essentially the Strickhart's his work on BMO Sobolev spaces. But in fact, somehow it's strictly stronger because the Murray result says R-lib is good enough to solve the Dirichlet problem, and Kaufmann says that regular parabolic lib is not. All right. On the other hand, so somehow the difference is subtle. But it's also significant, right? Because
Steve,
yeah.
Could you write it slightly larger?
I'm sorry, what's that?
If you could write slightly larger letters.
Oh, slightly larger letters. Yep, sure.
Thank you.
Yeah, okay. All right, so the difference is subtle, but it's significant because, I mean, for the one, you can solve the Dirichlet problem, this one you can't. All right, and then there are other differences. For example, it turns out that if you have a graph of just a Lipschitz function, it's actually going to improve to be R-lib if and only if all nice parabolic singular integrals are bounded on L2. All right, and so also in particular, this says that if you think about, for those of you that are familiar with the Davidson's theory of quantitative rectifiability or uniform rectifiability, you can talk about the parabolic analog of that. And what this says is that for a parabolic Lipschitz function or Lipschitz graph, sigma, we have that sigma is parabolic, uniformly rectifiable, is a scale invariant quantitative version of rectifiability introduced in the elliptic case by David and Sons, developed extensively by them. If and only if it's actually R-lib. Okay, so when you're talking about parabolic quantitative rectifiability, just being Lipschitz is not good enough, you need this R-lib doctrine. Okay? All right. So this brings us up to the result that I want. For example, over the course of these lectures, which is the following thing. Given these two results, the counterexample of Kaufman and Wu and the positive result of Lewis and Murray, it's natural to conjecture that this R-limit condition is not just sufficient, but also necessary for the solvability of the Dirichlet problem. Okay, and so that's the result that we're talking about. All right. So here's the theorem. This is joint work with his side boards. Tom Martel, Van Eastrom. All right. So, oh, and by the way, just for the sake of simplicity, this is not really essential, but because this reverse Heller condition is a local scale variant estimate, so you can localize it. But just for convenience, I'm just going to consider the case where the domain is a pure graph domain. So the domain is going to be the region above this parabolic Lipschitz graph, okay, infinite Lipschitz graph, okay? So let A be parabolic Lipschitz. We're going to set omega to be just a set of, let me write it this way, y naught ys such that y naught is bigger than a of ys, okay? And we assume that the harmonic measure, or the caloric measure, and adjoint caloric measure. So that just means the same thing as caloric measure, but for the adjoint heat equation. dTu plus Laplacian u equals 0. All right? Suppose that these both satisfy the A infinity problem with respect to sigma. Okay, I'll define this in a second, but this A infinity property is equivalent to the reverse Heller property, but in a certain moment. Okay? All right, and then the conclusion is that sigma, which is going to be the boundary of this guy, is R-lit, or A is an R-lit function. Okay? All right, so let me try to provide a little more motivation here, and then also to give you sort of a preview of how the proof goes and what the key idea is. Oh, by the way, maybe I should define A infinity. A infinity just means that if I look at, so I'm given a surface ball or surface cube delta, defined as I did before, and a Borel set, contained in delta, and I have that omega of A over omega of delta is less than or equal to some uniform constant times sigma of A over sigma of delta to some positive power beta, which again is a uniform exponent. Okay? So this is, notice that this is a scale invariant quantitative version of absolute continuity. Okay. All right. So this result, this converse of Lewis-Murray. Oh, by the way, maybe I should say something about the fact that we have to assume both the property of A infinity for both the caloric measure and the adjoint caloric measure. Notice that Lewis-Murray's result also gives the result for adjoint caloric measure as well, simply because the class of domains under consideration is invariant with respect to the change of variables t goes to minus t, which match the heat equation to the adjoint heat equation. All right, so Lewis-Murray also holds for the adjoint heat equation. Okay, so this is a converse of the Lewis-Murray result. It's an interesting question whether theorem could be true for assuming only the result for the caloric measure. Notice that because of Lewis-Murray, what that would say is that knowing that the caloric measure is good, automatically that gives you that the adjoint caloric measure is good. I would say that it's R-lib, and then you go Lewis-Murray for the adjoint caloric measure. Okay? That could be true. We don't know how to prove that. All right? So this is the version that we want to prove. All right? So to put this in a little more context, this is in the nature of a certain class of free boundary problems. Going back to Hofmann Caparelli. So the idea is that you have some positive solution U on one part of a free boundary. The free boundary is actually the level set where U is 0, and then you know some good things. So notice that if U vanishes on this free boundary, then the inner unit normal derivative of U is just the length of the gradient vector because the tangential derivatives disappeared. And suppose that you know, so the idea of the free boundary problem is that suppose you know good information about du dn, normal derivative. Does this give you good info about the free boundary itself? Okay? And so notice that this is really related to quasi-kernels because you could think of U as being a Green function, right? That's a solution that vanishes on the boundary. And then du dn is just the quasi-kernel. Okay? So you're assuming some regularity about the quasi-kernel. What does it tell you about the regularity of the boundary? Okay, so results of Alton Caparelli. And also sort of a sharpened version of this due to Jerison, say that if log of k being the quasi-kernel, is in C alpha, or lip alpha to use the notation I was using before, this implies that the boundary, this is the free boundary, is in C1 alpha. Or to put it another way, that the unit normal is C alpha. Okay, I'm cheating because there's some background hypotheses. There's a background hypothesis right for the class. And there's a sort of an endpoint version of this. due to Koenig and Toro, which is that, again, the background hypotheses of right order flatness, that log of K is in VMO implies that the unit normal is in VMO. VMO being the space of vanishing in oscillation. Okay? There are also caloric versions of this theorem. There was a preliminary version due to John Lewis and Kai Nystrom and me with an extra hypothesis, which was then removed. The sharp version is due to Max Engelstein, who basically looked at a true parabolic version without any extra hypotheses of the final Koenig-Toro result.
Steve,
Yeah.
what hypothesis did you remove? What hypothesis?
Asymptotic optimal doubling.
What?
Asymptotic optimal doubling.
Oh, okay.
That was not needed.
And what are you asking of you here?
It's a solution. Okay, so for these results, it was a harmonic function, and in the parabolic setting was a solution to the equation. Just 3 minutes. More. So, just give me time to sort of summarize. Give us a good place to stop. I need to get this thing right again, but we're almost done, so let's go with this. All right. Okay. So, let me just summarize to finish this lecture by discussing a bit of the idea of the proof of the theorem I'm going to show you, which is, I just erased it, but then we're going to discuss. Okay? So, notice something here. This is, again, think of U as being a green function, right? And so the information that you're given is somehow you're given knowledge of the normal derivative of the green function at a particular level set of the green function, the level set where U is identically 0, okay? So what we're going to do is to look at more generally interior level sets of the green function G. When we come back, we'll talk a little bit about what G really is. This will be with some fixed pole and normalized. And so let's say sigma R is a set of points x and t such that E of xt is R. We're going to view these level sets they're going to be viewed as extensions of the original boundary, which is sigma 0, right? That's the original boundary that the green function manages, okay? All right, and then, so these extensions, you could think of them as being sort of substitutes for taking an average at scale R of the graph function that defines the boundary. And then we're going to prove sort of Woodward-Paley type square function estimates for these extensions, for the level set sigma R. Woodward-Paley estimates that sort of view them as extensions of the original boundary. And then we use those Woodward-Paley estimates to establish the R-lit condition. All right? So that's the idea, all right, that underlies, this is really the key idea to everything that we're going to see, all right? But first we're going to lay some groundwork. That'll take a little while. I guess this is probably the right time to stop. Yeah, I've run a couple minutes over, so let's stop now. Before we go, do you have any questions?